morning and welcome to the EE Department Colloquium. Today's speaker is Professor Mohamed El-Sharkawi, whom most of us have known for many years, at least since 2000 for me, when I joined here as an assistant professor. Professor Sharkawi is a IEEE fellow. He finished his PhD in electrical engineering from University of British Columbia in 1980, and he joined the department in 1980. He's a professor in electricity and power engineering side of the department, and he has been instrumental in maintaining, building, and sustaining that group for the last 35 years. He's a key member of many aspects of IEEE society level power systems as well, research, as well as organizing several meetings. He's one of the founding members of the neural network application to power systems. He is also a world-known author and also lecturer for several summer programs as well as the international conferences and meetings. He's a founder of multiple IEEE societal level programs, including conferences, including IEEE Computational Intelligence Society, where he was a vice president for technical activities. He was a founding chairman of several task force, working groups, and subcommittees, which includes the IEEE PES subcommittee on renewable energy, machines, and systems. He is the author of 4 textbooks, which are in multiple editions and widely used, I believe. One of the tasks that he is thinking about doing is to further improve the books. About Mohammed's book, we can safely say that he foresaw the direction in which the field will go. So this is a comment I typically hear from outside members of the power system community, saying many of his books were well ahead of their times in terms of projecting the area. Professor Sharkawi is also an excellent teacher. The record that we all aspire to follow, and I often ask him how he does it seamlessly, and he is also an incredibly good mentor for his students, and the relationship he has with his graduate students is an example for many of us, other faculty who are here and try to follow his example. Professor Sharkawi recently received, appropriately, the 2014 IEEE Outstanding Educator Award, and he also received recently 2015-2017 3-year program of International Fulbright Fellow. So this he is going to leverage to help developing or friendly developing other nations in terms of renewables energy. He could probably tell you more about it at a later point. With this, I introduce you to his topic, Outlook into Modern Engineering Education. Mohamed.
Thank you, Professor Pabandra. Good morning, everyone. My talk is actually, I was thinking giving a talk on research or giving a talk on education, but Professor Jianning Huang, he said, let's do education. So you asked for it, all right? So before I start, I truly believe that we as electrical engineers, we are responsible for the civilization we live in. And if it's not for us, I think we'd be still living in caves and eating raw meat. By the way, some people, when I say that in the past, said, oh, we like raw meat. What's wrong with that? So I think we are the gems of the society. So to start with that, just give you some uplifting and just to feel good about the profession that you guys are in. No matter what field of engineers, however, electrical engineers are the best. Yeah, so this, we actually enjoyed this reputation for quite some time. But then recently, We are being accused of a number of things. And the list can grow long and long and long and long, and they actually dump it on us that we engineers are now don't let people sleep well, for example, addiction, right? And stuff like that. So this is the status of engineers. So we cannot really live in our ivory tower anymore, okay? We have to go down to earth, and we have to address these issues. In addition to that, if you look at the industry, what's happening in the industry right now, the industry has seen a lot of changes, really a lot of changes. And I'm going to just mention a few of these. For example, you have global competition. You cannot really design your product in isolation and under protection. Doesn't exist anymore. So there is a global competition. Once there is a global competition, it has an implication on workforce, it has implication on quality, it has an implication on economics. The other thing is that there is restructuring and downsizing of industry. All industry are going through that, okay? And that, of course, results in lower workforce in the United States specifically. Although that trend is getting better right now, it's improving right now, but this is the case. And one example of that is utilities that were known for not let anybody go after they did the restructuring and develop and divide themselves into mainly 3 components. We have seen a lot of people who were pushed out. Now, also, integration within the utility. Every now and then you can see that the management structure has changed from horizontal to vertical, then vertical to horizontal, horizontal to vertical, keep doing that. And now we are in the horizontal integration. So what does that mean? It means that every engineer in the past, the engineer, if you go vertical integration, engineer will talk to his boss, which is engineer, might understand him, and his boss talking to his boss, who is semi-engineers, so probably can understand him, and so on. But right now, the engineer has to talk directly to the people in higher areas or higher levels that may not be engineers. Also, the industry has fragmented. Now, the model you see right now, the GE model, General Electric model, where they build everything from the jet engine all the way to what? Toothbrush, okay? Electric toothbrush. That model, you're not going to see it surviving for long. Industry is breaking down into smaller components. This way would be easier managed and easier compete. Also, the good thing right now is that lots of development, great development that was done in the defense, as part of the defense work, is now available to us to use in the civilian life. GIS, GPS, you name it, all that stuff that was restricted to the defense is now available. So that's good news. Also, we have explosion of information technology right now, which is really, really great right now. In your fingertip, you can get information that you can get information in minutes that used to be months before to get this information. Okay, so based on that, it looks like products can no longer be designed in isolation. You have actually to use complementary products. Example, Boeing 787. How many products from how many countries were used to assemble that? That's going to be the model in the futures. And you're going to see companies will opportunistically collaborate, okay? Where 2 companies can work together to produce a certain work. Why is that important? We're going to see that later on, because we have to reflect this new environment somehow in our curriculum. Also, joint ventures is actually the dynamo of the economy of any countries. And they always produce innovations, new designs, new manufacturing skills, you name it. So, and it is obviously that lots of our engineers, our graduates, will be working in a small organization rather than big organization. We see that. So what is small organization? Well, we'll have narrow focus. For their focus is very narrow in one certain area. They may depend on complementary product coming from different company or even different country for that. And for them to survive, they have to keep defining new customer need and produce it. Example, a cell phone. Cell phone, the objective of cell phone in the past was to talk to someone. Now, see what you can do. We had actually an IEEE meeting, and we were showing in that IEEE meeting all the equipment, historic equipment. And one of the display that I put there was a cell phone. I put the cell phone here, and I put what that cell phone replaces. And what the cell phone replaces took about 2 or 3 tables just to fill what that phone is replacing now. And this is happening because a company has to find a new need. I need to get you audio so you can buy it. I need to get you video so you can buy new models and so on. New applications. And the small organization, because they are small, they may not have the budget to hire public relation people. So they rely on the engineers to do that. So effective public relation is going to be important. Remote engineering, you produce something, you're probably going to produce it with people totally outside the country. So how you deal with them, that's remote engineering, joint venture. And again, small companies, they don't have the capability to hire a big workforce that can deal with issues such as contracts and just contracts between companies and so on. So they rely more and more on engineers to look into that. Now, so the new engineers that need to really be produced, okay, to meet industry challenge. When you go and talk to the people in the industry, they will give you a list, a very long list, what they want the engineers to be. And we're going to see the challenge here. So pretty much, they want you to be, number one, able to communicate. That is number one issue for them before they even get to the technical. They say, when I have an engineer talking to non-engineer, most of the time the non-engineer doesn't know what the heck is this guy talking about, why it's important, okay? And for that, there was too many good products that was not allowed to be produced at large scale because the engineer could not convey the importance of this. For example, the person who invented the SCR, silicon control rectifier, that's a device. He couldn't actually convince his upper management that this device is important. And I'm not going to mention the company. If you go Google it, you will find the name of that company. So the upper management said, oh, I don't see that there is importance to this. Now, what happened is Japanese firms took that idea. And now it is a billion-dollar industries, billions of dollars of industry. In your home, look in your home anywhere, your fridge, your washer and dryer, your heater, you name it, they have that device built in this equipment. So, and they attribute that is that the engineer could not really communicate the importance of this. Of course, industry, they don't need to be people up to date. They need them to be up to the minute, have up to the minute capabilities. And they need them to be creative thinking. They like the engineers that's always look outside the box. So they want the engineer to always look outside the box because that's where all the creativity happening. Now, the other thing is that we need teamwork. We need to have people that can work together in a team. Now, this is an issue. However, that issue is slightly being addressed right now. If you go to any company, name a company you want, engineering company, you will notice two things. The first, the people who have the window offices are the lawyer, the management, and the economist. And the engineer, they give them desk beside desk beside desk and just sit there, right? Or give them a cubicle. So engineers tend to be comfortable when they are in their own space, cubicle. Why? Don't ask me why. And that actually creates a problem where you can see redundancy in the production happening or redundancy in the innovations that happen in companies. Teamwork is very important, and they always talk about that. We have to teach our students teamwork. I think our design classes, capstone design classes, are designed really to address this issue. Also, they need quick learner. Here in the university, we tend to spoon feed our students. If they don't understand the first time, repeat it. If you don't understand the second time, repeat it again. If you don't understand, come to my office hours and keep doing that. You go to the industry, they tell you that. If you don't understand it, get out of sight. So it is a quick learning is very important. Now, we have to be sensitive to and knowledgeable of the societal and environmental impact of our products. And they require the people to have multidisciplinary background. You're going to see later on that these are conflicting objectives. You might as well, those of you on optimization, you might want to look at Pareto front for that and pick something from the front. You can see a lot of objectives are in conflict. Of course, effective mentoring. So what does that mean? That when you are hired or a new engineer hired, in short time, they would like that engineer to start mentoring others. And leadership skills and management skills, whatever that would require. They require the person to be well organized and have entrepreneurship capabilities, because they can look at this and they can figure out what could be the next big thing. Interaction with court laws and expert witness. I worked as an expert witness. And the thing that I hear from the lawyer on and on again is that they really hate to have engineer as an expert witness. And we ask him why. He said, this guy talk about something that nobody in the jury box would understand. They cannot bring that material or information to the level where the general public will be able to understand. That's, again, the issue related to communications. Knowledge of patent and intellectual property, how many companies were bitten because they were not aware of patent that's out there and reinvented the wheel. So that is important for them to know. So is the standards. And so what is the bottom line? The bottom line is tell you that if an engineer insists on remaining strictly technical, that engineer is not valued anymore. So they need much more than just only the technical capabilities. Okay, so this is a picture that we are facing. All right, so how can we address that? What are the components that we can add in our curriculum to address these, or even most of these if we can? So the first thing, environmental. We have to impose the environment in our design. So whatever you do in the capstone design or any design classes, we have to address the environmental issue of that somehow. We also have to address the economics. of the product because, again, global competition. We have to address manufacturability. How you manufacture that? You have an idea how that idea is manufactured. That's a manufacturability issue. How is that done? Is it sustainable? Or this is something that will last for 2 weeks until the people buy it and then throw it away? Is it something that will be sustained? Health and safety, this is something that we don't really address. Do you know how many universities in the United States, electrical engineering, I'm talking about four-year school in the United States that teaches electric safety? Can anybody guess? Zero. So isn't that something that needs to be somehow addressed? Ethics. Of course, ethics is very important issues. And ethics is actually, can be very obvious lots of time, but may not be that obvious some other time. So for example, you are an engineer, you're going to build something that will be delivered in January, right? So you are using the code that is available. But you as an engineer, you know that the code starting February will change. And if you build it based on the code in February, that's going to cost your company a lot of money. Would you still build it with the old code or with the new code? That is an ethical issue. So some of that stuff is not that obvious, but it is there. So we need really somehow to talk about these things. Societal impact, what is the impact of other, and political impact. I'm going to give you an example of that. When you see an issue that related to health being discussed on TV, who would be discussing that? Doctors, right? When you see illegal issue discussed on TV, who would be discussing that? Lawyers. When you see an engineering issue being discussed on TV, very rarely you'll find engineers discussing that. It's actually there was one case they were discussing, for example, the effect of magnetic field on health, and what they have people talking about that. It was a kid that's 18 years old and his mother. We're talking about that on TV. So there was no engineers there. So another scenario. For some reason, engineers shy away from the political activities. And how many engineers we have as a president of the United States, right? Carter. Do you remember anyone else? That's only one, huh?
Herbert Hoover.
Okay, 2 out of how many? Okay. So we don't have that many. In the 70s, I think it's in the 70s, where the Congress passed a law that called PURPA Act. That was an act of Congress that forced utility to buy electricity from renewable resources producers at their avoidance price. That sounds like good law, but no engineer were discussing that law. So what end up with 2 major problems. The first problem is that they based their tax credit on installations. So what does that do? You can see when you go to Tehachapi in California and all that, at that time you see a lot of wind farm, but no machine inside. Because this is installation, not necessarily production. The second issue, there was no engineer talk about reactive power. Those machines will deliver maybe 1 megawatt of real power, but consume over 1 megavar of reactive power. So utility will pay them for this, but don't charge them for reactive power. Reactive power causes all sorts of problems, flickers. The customers will have flickers because of that, but who they complain? They complain to the utility, not the development. So we were not involved in that. coordination with complementary product, and the knowledge of standards and regulation. This is very important, actually. And in all design classes that we have, capstone design should have this component about the standards and regulation. Okay, and Professor Rich Christie keep hammering us with that, and that's right. We have to know this. And we have to look if our product, even so we're still a student, if our product really gonna violate any of these standards or regulation. Available design tool and the marketing. These are the two things. All right, so based on that, let's look at the learning environment. So these are, I just covered the issue with industry and what they want. So what are the challenges for us as professors, as faculty? We know that we have high demand in new areas, and we don't have necessarily faculty in new areas. I'm going to give you an example. Solar energy is becoming #1 growing industry. We don't have a single faculty that will provide expertise in this area in terms of teaching. We don't have that. Most of the students, again, our students work while they are studying. So they have actually extra burden on them, and the time that they have to digest the material is less than those who are full-time students. Our classes are large, and that actually prohibit or actually reduce the interaction between the faculty and the student. And we tend to cover more material per unit time. This is a given. As a faculty, it's a given. And we don't really have, I'm talking about UW, I'm not talking about UW, I'm talking in general in education. There is not that many specialized laboratory. As a matter of fact, there is a dangerous move, in my opinion, I'm an old guy, that we replace hardware lab with computer simulations. That, in my opinion, is very dangerous. Curriculum is stagnant. I'm not talking about us, but I'm talking in general. You go to school, look at maybe the class in one subject, look what was the material that was taught 10 years ago and now, you probably are not going to see that much change in that. And the industry is impatient. They start developing their own training, and that's dangerous. If the industry is going to do the education part, then we are not really doing our job. And there is no monopoly in education anymore. The world is open. You can now get your education from anywhere. There is no monopoly. So the other issue is what's fundamental. I'm going to address that a little bit on. If I tell you what's the fundamental of electrical engineering, how many people we have here, maybe about 100, I'm going to get maybe 200 opinion for that. And also we have a tension between depth and breadth. Sometimes say it's better to have a broad education. Sometimes say, no, we need to have a depth in our education. If you look at curriculums, they are clogged, really clogged curriculum. And we also have the phobia of not covering everything. You say an electrical engineer will graduate and he doesn't know what is the reactive power? Yeah. If he's not going to work in power, he's probably not going to need that. So we have the phobia of covering everything. And instead, we have to really teach the student how to learn. We give them the capability that on their own, they will be able to acquire new knowledge. Instructions, we may want to do modular instruction. This model of modular instruction is very, very helpful. We tried that for a group, for a number of classes that we offer that the Department of Energy gave us fund to develop, and we did that on a modular instruction. So student can take a module rather than a course. Take a module here, module here, module here. They may not need to take the whole thing, modular instruction. Is that possible? We need continuously to merge research with undergraduate education in a number of ways. And we need to integrate the curriculum and using modern technology. And I believe that we should extend the academic year, and we're going to talk about that a little bit later on. So if you want to address what's EE fundamentals, when I was studying electrical engineering about 5 centuries ago, this was electrical engineering: energy, electronics, control, electromagnetics. Now you look at electrical engineering, we have AI, image and voice, nanotechnology, photonic, communication, medicine, chemistry, keep adding, adding, and adding. So if this is, now this is the electrical engineering. So when we define the fundamentals of electrical engineering, we cannot define fundamental based on this, but perhaps based on this. So if you do that, then how you do it? What is the fundamental subject that will address all these areas, or most of these areas? That's hard. If it is not that hard, if you manage to make it, then you're not going to be able to finish what you would like to achieve in 4 years. There is no way that you can achieve that in 4 years. So this is a fact. This is a fact. I was just talking to Professor John Czar, when he started to craft our core curriculum. And then he said, well, it looks like it's very difficult. Let's get only 2 or 3 courses as a core. I fought him hard for this. And I was totally against him, but now I can see that he had a point. What is a core? We cannot really define a core that satisfies all this area. So I have some scary thoughts that we might want to consider. Why we aim at covering everything? Why do we aim at that? Why a student must have the necessary background for any EE job? Now, should the student have the ability to learn on their own? Actually, that's what we should do. We should teach the students how to learn. And then, are we really providing a student with vocational skills? That's what the industry wants. We want vocational skills. That, if you said yes, then you are in the group who said the objective of education is to prepare the graduates to the workforce. And that's what the industry wants. We want to get people that can directly work in their facilities. If you are among the group that said no, which is a very growing group now, they said vocational skill may have short longevity, very short longevity. You can see a lot of examples where fields were vanished. Okay, they were here for a while and vanished. Said, well, it's more important that we teach our students and how to learn on their own. Okay, so should the undergraduate program put less emphasis on theory that are well developed but are not encountered in engineering practice? I'll give you an example. We teach circuit theory. We love to give problems to the student where we have multiple branches and multiple nodes. Series, parallel, series, parallel, series, parallel, and cross, and Y, delta, and all these branches. And then we said, okay, we're going to put the source here, calculate the current here. If they come to you, tell me which device you know of that has circuit like that. Okay? Well, the neural network people now can say, yes, we have a device that can like that, but that's small group, right? So is it really, should we go back and maybe free ourselves from what we have learned and try to see if we can make a change into the curriculum that address that? The other thing is that we emphasize formulas a lot. From my experience, my student, and I have a lot of them sitting here, they will do very well in the exam. They're probably going to get the full mark. And then when I see them in the next quarter, I ask them, okay, now how do you calculate this? Totally forgot the formula. So their memory is more of a RAM memory. that end with the exam, it's erased. Okay? Now, I'm not saying all of them, but this is a fact. Anybody dispute this? Okay. So, but when I ask them, what is going to happen if I increase the voltage here? What's going to happen to this guy? They know. They know that what happened. Okay? But they cannot relate maybe the equations that this is related to that. But they know how to get that equation if they need it. So what I'm saying is that we should really emphasize concept, graphs, rule of thumb quite a bit in our classes. The other thing, again, segment the curriculum into smaller modules. And can we really extend our undergraduate education? 4 years is not really enough, especially with EE that broad. Even 5 years is marginal. But oops, we're going to be against what the European Union are doing. You know their engineering school, how many years is their engineering school now? Can anybody guess? 3 years. You get an engineering degree. They said they put a lot of material that we give it here for the first year in high schools. So they go 3 years. Okay, now, what is the educational objective? Now, people are start talking, what is really the educational objective of undergrad and grad? Okay, they said undergraduate experience, this is opinion of a lot of people, and they're going to see more of that coming out. Said it's actually for prepare for graduate school. Number one objective, prepare those guys to go to graduate school. That's good business for us, right? That's good business model. We always have customers. And prepare for who want to go to other field. Want to be lawyers, doctors, and all that with some engineering degree. All right, so, but how about workforce? Master degree. That for the design engineering career. Okay, that's where you go really deep into the material. How about the PhD? Just produce professors, researchers, and experts in the field. So you can see a lot of people are going to start talking about that. They're already talking about this. How about the student we have? Well, our student might always be entertained. If you don't entertain them, half of them will fall asleep, the other half will faint. And sometimes very difficult to concentrate. If you have a TV, you have kids, let them watch the TV. Turn off the TV, ask them what they were watching. Sometimes they don't know what they were watching, just staring at you. So I can see in my class somebody staring at me like this. I know that the brain is somewhere else, okay? They don't have patience. They use by click, they get what they want. So now, if you give them maybe a problem that maybe needs few steps and thinking, they don't have patience for that. Now, also, when they don't want to understand, they find it's easier to memorize. If they want, it's easier to memorize. And I find in some situation, they have very weak engineering judgment. I remember I have problem for a student, tell them to go and calculate the losses in a transistor. It was 10 amp transistor. The guy came up with 10 to the power 16 watt. And I said, well, isn't that too high? He got his calculator. Yeah. Are you sure? Yeah. I asked him, go and see if Grand Coulee Dam is big enough to power your transistor. So this, we see that. Fantasize. Oh, their brain goes far away. And keyboard engineers. They really believe in keyboard engineering. And maybe intrigued by high-tech toy, and that's what we should do. So for learning, I think it's, my time is 5 minutes, good. Is classical instruction, based on all this, is classical instruction slowly disappearing? Is it still the right model for the new generation of students? Should we teach the student how to learn? Should we encourage interactive cooperative learning? That's where they learn a lot. Actually, at least my students, they will tell you that they learned from the design project way more than what they learned from the lectures, okay? And maybe because of the time, I'm going to just address one more issue, is that in our undergraduate education, historically, we depend on three cognitive learning. Knowledge, the student will learn, the student will comprehend what they learn, and the student will apply what they learn. That is the model of undergraduate education. What we should do really is should add to it the higher level, which is analysis, evaluation, and synthesis. Evaluation and synthesis. Those are kept for graduate studies, but actually should bring that to undergraduate as well. So you look at people, they said, those are famous people, said, I never teach my pupils. I only attempt to provide the condition in which they can learn. Education is what remains after one has forgotten everything he learns in school. Who said that? Albert Einstein. Okay? And also the Chinese, they have really very famous verse, and I think I destroyed it by maybe my poor English. It said, if you give me a fish, you feed me for a day, but if I learn from you how to fish, I can feed myself for a life, and that's what we need to do. All right? So engineer for the new century, you have to be a super engineer, and you have to know all that stuff here, and thank you for listening.
Mohamed, thank you very much for excellent talk.
Thank you.
Any question to Professor El-Sharkawi?
So they agree?
They are thinking. Yes, Linda.
I have a question. So UW has an honors program, which we looked into for my kids. How does that go along with what you're saying? Because I don't see many honors students in the engineering program. But what they do have is more interdisciplinary type of focus. What is your feeling for kind of opening up engineering for the UW honors?
I think who would object to that? That's a great idea, but why engineers are not in that program, you said? Not that many. Why? I'm not aware of this. Anybody here in the honors program? Yeah, I agree with you. But how to do it, I don't know. Yes?
I'm thinking of, yes, we want our students to learn themselves, and it's a life learning experience. But at the same time, in the first couple of years of their undergraduate study, the way we evaluate them is based on exam. We cannot ask all students to do capstone in the first couple of years. So we only can exam them. We need to give them grades. And because our exam normally just for a large class, we just have 15 minutes or 1 hour, how can we come up with a good evaluation system so that they know how to learn themselves instead of memorizing it?
Yeah, this is tuned toward the later junior and senior classes. So when you go to the fundamentals, math, physics, chemistry, and all that, because of the large number of students, you don't have that much room to do things differently than what we're doing, unless you add to it some kind of an extracurricular activities and maybe distance learning, stuff like that that can help them. But what I'm talking about here is that really the later part of junior and senior student in our classes. Yeah.
How should industry respond to the challenge that we have for education?
Yeah, that we talked to them about a lot of time. They said, oh, we'd like you to do this and this and this and this. That's their list. So normally I provide on my list. And we'd like you to do this and this and this and this. Okay, you need to hire, you need to spend money on research, you need to do this, you need to do this. So this is very, very good question, actually. It's both ways. Now, the industry right now, they claim, and each industry is different. Okay, we cannot complain really about computer industries, right? Our building is built by them. So they support us quite a bit. But there's a lot of industry that they don't provide the support that they should. Energy is one of them, in my opinion. They don't provide the support that they should. That's because they fragmented themselves and they have very little funded for research right now. But they can help us in different ways. For example, we can use them in our capstone design. We can use them actually to come and talk to the students that are thinking about entering engineering. They may not be able to provide us fund for research, but they may be able to provide us fund for labs. My energy lab is an example. Most of the component in the energy lab was funded by industry. So you have to keep working with them. You have to keep working with them. Yes?
So you mentioned that you were sort of convinced that maybe just having 2 or 3 core courses could be okay, and that wasn't initially your thought. I'm wondering if you could describe more about how you kind of came to think that, because I can see that, well, whatever you're learning, it's, you know, the process of learning, but then also at 19 or 20, it can be hard to decide, you know, a track you want to go for your career.
Oh. Yeah, so now we're going back between breadth and width. Now, in the past, we have a very wide core in the EE. In almost every area, they have their own core. The idea for that is that the person will take the core for the area they want to specialize in, right? Now, what we did is that I think, in my opinion, went below that level. What we said is that leave the core, but it's not required from anyone. We're going to go one level below and say that these are the classes that will give the skills for most of these people. And then if you want to go to energy, then take the core course in energy, 351, for example, on that. But that core is not required for anyone to take. It's only for the people who get there. And I believe that this is a model. There is no way for you to have a core that covers all the disciplines that today we have. I don't think that you can make it. Unless we fragment our department seriously, and instead of electrical engineering, we can have energy department, right? Signal processing department, computer engineering department, and so on. Yes?
I don't feel that the quarter systems help us to learn, because I personally learned more sitting in classes than actually taking them.
Sitting in classes than actually?
Like registering in them, because like they're like too much like quizzes, homeworks, exams, and you feel like taking the time to learn and digest the material is like a luxury. Mm-hmm. So I end up like sitting in many classes, and I feel this is part why so they can't like.
Yeah, there was, I didn't have time actually to go into learning modes. You are not going to find 2 people who will learn the same way. No way. You're going to find people that like to look at the big picture, then zoom into details. Other people would like to start with the detail and see what is the big picture, for example. These people learn differently than these people, and so on and so forth. So the idea here is that there is no way for you to cover all these learning domains. No way. So what you do is that you try to cover something that can be suitable for most, and then allow additional instruction for these. We can use, for example, media, we can use internet, we can use all that can actually tune toward other type of learning modes. Yeah, but you have only one professor in the class, so.
You talk about having the core, but when you can't figure out where the core goes, and most of your teachers are going academic and not industry, so they don't understand. I don't want to say that they don't understand necessarily how you can apply it in industry, because some do, but some don't. How can you pass on that bigger picture to the students as they're trying to figure out where they want to go?
Okay. First of all, your first statement, I would argue with it. Okay? What I'm doing here, I'm doing research. Research for what? For industry, right? And that research goes to the industry applied. If I'm going to work for industry, what I'm going to do? I'm going to do research for the industry. That will be applied. So we're not really that far from industry in terms of knowledge and capability. It's actually, you can think that probably we're a little bit higher because we can dedicate most of our time to that than they have. We have more resources than they have. So industrial experience, we have it, even so we're in different building. I'm not at Puget Sound building, I'm here. But my knowledge, industrial knowledge, is very comparable to they have. So from that point, I don't think that the people, when they say academicians are not tuned toward the industry need or don't know how the industry works, I don't think that that's totally correct. The second part of your question is about the core, right? How the core is really, or how the field is really developed. If you look at any field, how it's developed. First, start as a research, right? Research project, and funded research. And then, if it's successful, it will grow. You can see more people are doing exactly the same thing. And when it grows, it becomes more stable in terms of knowledge. Now you acquire enough knowledge in that, and that knowledge is stable. Then this knowledge go into the curriculum. So, and this is actually, tell you the truth, this is what I love about United States. This is always the case in the United States. Look at any field that's being that. When it started with simple project. Internet, look at the internet when it started. It was a university simple project. Grows, and now it's part of the curriculum. I think this model is still the best model. If it dies, then you know that this technology probably is not all that great, and it's not included in the undergraduate, should not be included in the undergraduate curriculum eventually. Did I answer your question? Did I dance around your question?
I guess the question was more, I've gotten a lot more out of the examples that a professor has given me.
Mm-hmm.
And not all professors will do that. They will solely focus on this is how you do, say, nodal analysis, not this is what nodal analysis will do for you in the long run.
Ah, I see. So that goes back to the issue that I said, is that we should really rely less on formulas and more on concepts and rule of thumb. That's what I believe. Like, say, I don't think that I give any exam without letting the people come up with one sheet of notes. Put all the equation you want on that sheet. I don't care, okay? And the exams, it's, if I put exam, maybe conceptual or problem, I still let them use the equations, because that's, to me, it's good that they know where to get the equation later on. But it's more important that they know the conceptual thing. Yeah.
I think we will conclude the question session. Let's thank the speaker, Professor El-Sharkawi.
Thank you.